In this video, we are solving an advanced exercise on Newtonian mechanics. If you need a refresher on this topic, feel free to check out this playlist where I cover this subject starting from zero. You can of course also leave a comment if you have any question or suggestion. Let's get into it. Let's say that we have an upside down hollow cone, and within this cone there is an object making a circular motion along the inside surface of the cone. Now you can imagine that by making this circular motion, the object is pushed outwards and therefore prevented from sliding down to the bottom of the cone. And what we're asked to figure out is what is the minimal velocity of this object for it to make this circular motion at a specific height h above the ground for a cone which makes an angle theta with the horizontal plane. Now if we know the angle theta, then we know the shape of the cone. And this means that the height above the ground of the object, h, can be equivalently represented by the radius R of the circular motion of the object. So how do we now translate this physical situation to a physics problem that we know how to solve? Since we need to find the velocity and thus the dynamics of an object, the first step always is to identify all of the different forces that act on this object. And the first force, which is of course always present here on Earth, is the force of gravity, pulling the object straight down. Then of course we have the normal force, which is acted on the object by the inside surface of the cone, preventing the object to simply fall right through. And then there is of course the frictional force, which also prevents the object from sliding down. And this is much easier to imagine if you consider this angle theta to be much lower, and thus the slope being much less steep. Then, if there is a large interface between the object and the inside surface of the cone, there will of course be a frictional force preventing it from sliding down. Now that we have identified all of the forces acting on this object, let's lay out the strategy that we're going to use to solve this exercise and thus to find this velocity. The reasoning goes as follows. First, we restate the question and make sure that we understand what is asked. We need to find the minimal velocity v of this object such that it describes a uniform circular motion at a specific height h. Then we realize, because there is uniform circular motion, the net force on our object needs to be a force pointing radially inward, and that this net force is then the centripetal force, of which we know the expression, the mass of the object multiplied by its velocity squared divided by the radius of the circular motion. Then, taking a and b together, we conclude that we need to find the velocity of our object such that the sum of the three forces that we identified on our object results in a radially inward pointing net force, which will be the centripetal force. With this strategy at hand, let's now solve this problem. The second step is to realize that we need to add forces to get the dynamics of an object. And this is of course exactly what Newton's second law states. It says that if you add up all the forces acting on an object, it will be equal to the mass of this object multiplied by its acceleration, and thereby it links all the forces with the dynamics of an object. In this specific exercise, we have of course two dimensions. We have the radial dimension and we have the height dimension. And Newton's second law needs to be fulfilled in both of these dimensions separately. First, in the radial or the r direction, we have that the sum of all the r components, so the radial components of our three forces, will be equal to the mass of our object and the radial acceleration. Now we know that the radial acceleration will of course be the radial acceleration of uniform circular motion, of which we know the expression. So we get m times v squared divided by capital R. And this is of course exactly equal to the net force, the centripetal force, pointing radially inward. The exact same reasoning can be done in the height direction, or the z direction. We sum up all of the z components of our three forces, and this will have to be equal to the mass of the object times the acceleration in the z component. However, we stated that our object is making a uniform circular motion at a specific height h, and therefore it does not move in the z direction, it does not move height, and therefore the acceleration in the height direction, so az, will be equal to 0. So the sum of all of the z components of our forces will have to be equal to 0. So now we have two equations, which include the three forces acting on our object and the velocity that we're actually looking for. And to find an expression for this velocity, we are of course going to solve these two equations simultaneously. However, this means that we need to find an expression for the components of our forces, the force components, both in the radial r direction and in the z direction. And to find these components, we first identify some angles using basic geometry. First, the angle between the net force pointing radially inward and the surface of the cone, the dashed line here, is of course theta. Then, because our normal force makes an angle of 90 degrees with this surface, we conclude that the angle between the normal force and the radial direction is equal to 90 degrees minus theta. And to end off, the angle between the frictional force and the radial direction is of course theta. And of course you can see that I mistakenly wrote down 90 minus theta, but be assured this angle is theta. Now that we have identified these angles, we can write down the left hand side of our two equations, the sum of components of our three forces. First, we have the sum of the radial components. We have of course the radial component of the force of gravity plus the radial component of the normal force plus the radial component of the frictional force. And this has to be equal to the right hand side, which is mv squared divided by capital R. And because we did our preparation of identifying these angles, these components are very straightforward to write down. The R component of the force of gravity is of course 0 because it points directly in the z direction. The R component for the normal force is just the magnitude of the normal force multiplied by the cosine of 90 minus theta. And for the frictional force, we note that it points in the opposite direction, and thus we get minus the magnitude of the frictional force multiplied by the cosine of theta. And this of course has to be equal still to mv squared divided by capital R. Tidying this up and rewriting it, we get that the normal force times the sine of theta, which is the cosine of 90 degrees minus theta, minus the frictional force times the cosine of theta has to be equal to mv squared divided by capital R. And we already have our first equation down. Then we can do the exact same procedure, but now for the z direction. We have for the second equation that the sum of the z components of our three forces has to be equal to 0. Why 0? Well, remember that we don't have any motion in the z direction, and therefore we don't have any acceleration in this direction. Again, using our angles, we can very easily write down these components. For the force of gravity, we see that it simply points in the negative z direction, and therefore it becomes the negative magnitude of the force of gravity. For the normal force, we simply have the magnitude of the normal force multiplied by the cosine of theta, and for the frictional force, we have the magnitude multiplied by the sine of theta, and this has to be 0. Again, rewriting this equation and filling in that the magnitude of the gravitational force is the mass times the gravitational constant, we get our second equation. And now we want to use these two equations to solve simultaneously to get an expression for this velocity v in terms of parameters of our cone. Now we see, of course, that we still have this magnitude of the normal force Fn and the magnitude of the frictional force F mu. So we need to do a bit more thinking of what these actually mean. First, let's think about the frictional force. What is it? Well, it's basically the static frictional force. It's a force that prevents an object from sliding down. And the origin of this force is simply the fact that the surface of our object and the surface of the slope are rubbing against each other. For instance, if you have a car that is parked on a sloped road, then you know that there is the force of gravity that is pulling it down. However, since the car is not moving, preferably, you know that there needs to be an opposing force with equal magnitude, such that the net force is 0 and therefore we have no motion. But this opposing force is exactly the static frictional force. In our specific example, we have an object that moves on the inside of a cone. We have two things that keep this object from sliding down. First, we have the velocity from the uniform circular motion, But another part that is preventing our object from sliding down is actually the frictional force. Now, if you think of it, if there weren't any friction, then there would be only the velocity that keeps this object from sliding down. However, if you have friction, then you need less velocity to keep it at a specific height, because a part of the force that is needed to prevent the object from sliding down is now taken on by friction, and therefore you need less velocity. Now, in this exercise, we are asked to figure out the smallest velocity. So this means a scenario where the frictional force is as large as possible, such that it takes up the largest portion of the force that is needed to prevent the object from sliding down. Now, there is in fact an expression specifically for the largest static frictional force, which is equal to the static frictional coefficient μs multiplied by the magnitude of the normal force. And this is actually very good news, because this simple equation links the magnitude of the frictional force in our equations with the magnitude of the normal force in our equations. So if we take our first equation again, we can simply replace F mu with this μs times Fn, the normal force. So we get that Fn times the sine of theta minus μs times Fn times the cosine of theta has to be equal to m times velocity squared divided by r. And of course we see that the magnitude of the normal force can be factored out the two terms on the left hand side of the equality sign. And at this point we have an equation with the velocity that we're looking for, but still we have this magnitude Fn of the normal force for which we don't really know an expression. However, we still have of course the second equation, and if we also in this equation replace the static frictional force with the formula Fn times the static frictional coefficient, then also here we can factor out the magnitude of the normal force on the left hand side, and we can bring this factor with the cosine and the sine of theta to the other side. And this is exactly why it is so great to have two independent equations, because now we can simply fill in what we found from the second equation into the first equation. Substituting this Fn for what we find the following, that mv squared divided by capital R is m times g times the sine of theta minus μs times the cosine of theta divided by the cosine of theta plus μs times the sine of theta. As a final step, we can of course isolate the velocity v, and we find the following. We have that the velocity v is equal to the square root of capital R times g multiplied by this fraction, which only depends on theta, so the shape of the cone, and the frictional coefficient μs, which is a property of the material of the cone. And this is our final answer to our exercise. However, it doesn't stop here. An incredibly valuable skill to learn is to interpret the results that you've gotten and try some limiting cases just to get a feeling of the physics and as a sort of sanity check. In this case, we observe that this velocity depends on the capital R, and thus the height of our object above the ground, and the angle theta, and thus the shape of the cone. This all makes sense. Now, we see, of course, that there is also this frictional coefficient. Now, what happens if we have a frictionless surface, meaning that this friction coefficient is equal to 0? Now, this means, as we said before, that it is only the velocity of this uniform circular motion that keeps this object from sliding down. And this velocity now has a much simpler form. It's simply the square root of capital R, the radius of our circular motion, or equivalently the height above the ground, multiplied by the gravitational constant, multiplied by the tangent of theta, and thus the shape of the cone. So this all makes perfect sense, and you can play around with these different parameters to test your intuition of this physical system. One way, for instance, is to see that if you have a frictionless surface, you will never be able to do this trick if you have an angle of 90 degrees, meaning just a cylinder and not a cone. Now, of course, a follow-up question would be if this would be possible if you indeed have friction. And that is something that I will leave for you as an exercise. And this brings us then to the end of this exercise. Of course, as always, if you like this video, you can give it a thumbs up, which gives me some feedback to see what the audience actually likes and what not, or what it wants to see more of. You can of course also leave a comment to drive up engagement, or if you have any questions. If you really like this and you want to see more in the future, you can of course consider subscribing. And with that, I thank you for watching. I'm proud that you sticked out to the end, and I will see you in the next one.